You know, have you ever looked at a massive string of numbers and a calculation and thought to yourself, wait, how precise is this really? Well, welcome to this explainer. Today, we are tackling the deceptively simple world of significant figures, or as we're going to call them, sig figs. Think of this as your ultimate rulebook for managing the sheer messiness of real world data. Trust me, once you get this down, it literally changes how you look at numbers. Here is our roadmap for today, just so we don't get overwhelmed. First up, the rules of counting. Then we'll do a quick sig fig quiz to test ourselves. After that, we're going to look at multiplying and dividing, and finally, adding and subtracting. Simple enough, right? All right, section 1, the rules of counting. We're going to start with the absolute easiest rule before getting into the tricky stuff. So, our foundational rule is beautifully straightforward. Every single non-zero number is a significant figure. Boom. Done. Take a look at the number 846. 8, 4, and 6 are all non-zero, so that is exactly 3 significant figures. Or what about 3,546? 4 non-zero digits, so yeah, 4 significant figures. Pretty easy, right? But, well, it couldn't stay that simple. Enter the main antagonist of our explainer today, 0. 0 is the ultimate rule breaker. It's this tricky little digit that behaves completely differently depending on its exact placement. Whether it's leading the pack, held captive right in the middle, or trailing at the very end, its position changes absolutely everything about how we measure precision. Let's break 0's behavior down into 3 distinct categories. First up, we've got captive zeros. These are zeros squeezed right between 2 non-zero numbers. And good news, they are always significant. So a number like 704, that has 3 significant figures. Easy. Second, we have leading zeros. These are the zeros hanging out to the left of your non-zero numbers, like in 0.075. The rule here, they are never significant. In 0.075, only the 7 and the 5 actually count, so that's just 2 sig figs. But then, third, we have trailing zeros. Zeros off to the right. And for these, well, it depends. And this is exactly where people get trapped. And this brilliantly illustrates the trailing zero trap. Take the number 500. There's no decimal point anywhere. And because there's no decimal, those trailing zeros are not significant. It's just 1 sig fig. But if we change it to 500.0, adding that one tiny little dot, suddenly those trailing zeros are significant. Every single digit counts now, giving us a total of 4 significant figures. It's kind of crazy, right? The mere presence or absence of a decimal point dictates the entire physical reality of that number. Moving right along, section 2, the sig fig quiz. Okay, let's take a quick pause and see how these rules apply to some actual numbers. I want you to try and figure these out before I reveal the answers. 4,250, 7,080, 0.08060, and lastly, the absolute monster, 750.06480. Keep those rules of captive, leading, and trailing zeros in mind. All right, let's walk through the reveal here. 4,250, that's 3 sig figs. There's no decimal, so we just ignore that trailing zero. 7,080, also 3. We count the captive 0 between the 7 and 8, but we ignore the trailing one because, again, no decimal point. For 0.08060, it's 4. We ignore the leading zeros, but we absolutely count the captive 0, the 8, the 6, and that trailing 0 because there is a decimal. Now, what's really interesting about this slide is that final monster number. 9 significant figures. Why? Because there's a decimal point present. That means the trailing zeros count, the captive zeros count, the non-zeros count, the whole shebang. Everything counts. Okay, section 3, multiplying and dividing. We're not just counting numbers anymore, we're smashing them together. Now, when you multiply or divide, you follow 3 operational steps. Step 1, just perform the raw calculation on your phone or calculator. Step 2, look back at the original numbers you used and determine which one has the least number of significant figures. Step 3, you round your raw answer to match that exact least number. I know that sounds like a lot, so let's slow down and look at an example to make sure we've really got it. Here's our raw calculation. 5.64 multiplied by 12.458. Now, if you punch that into a calculator, it spits out 70.26312. But we know for sure that's not our final answer. Look at our original numbers. 5.64 has exactly 3 significant figures, 12.458 has 5. Our target is the least of those, which is 3. So we need to round our massive calculator answer down to just 3 significant figures. We keep the 7, the 0, and the 2, but then we have to look at the very next number, the 6, to decide if we keep the 2 or round up. Since 6 is 5 or more, we got to round up. And there is your final answer, 70.3, a perfectly precise, visually satisfying reward for surviving those complex calculation steps. It has exactly 3 significant figures, which matches the least precise number we started with perfectly. All right, final stretch. Section 4, adding and subtracting. Fair warning, the playbook totally changes here. I want to strongly emphasize the fundamental difference here so you never mix these up. With multiplying and dividing, the focus is on the least total significant figures in the entire number. But when we are adding and subtracting, the focus is only on the least digits to the right of the decimal point. Actually, scratch that. It's literally the only thing that matters. The total number of sig figs goes completely out the window. It's all about those decimal places. To master this, we're going to use a highly visual hack. I call it the line draw technique. Step 1, stack your numbers vertically. Step 2, find the number with the least digits to the right of the decimal point. Step 3, draw a hard vertical line right after that shortest decimal. And Step 4, after you add everything up, just round your final answer right at that line. Let's set it up. 4.328 plus 13 plus 5.45. If we just add them normally, we get 22.778. But let's look at the numbers. 4.328 has 3 decimal places. 5.45 has 2. So the crucial point is the integer 13. It has no digits to the right of the decimal point, 0. So imagine stacking these up. You would draw your hard vertical line immediately after the 3 and the 13. That means our final answer can't have any decimal places either. We look at our raw answer, 22.778, and we look at the digit right after our imaginary line, the 7. And because 7 is greater than 5, we round the 2 up to a 3, leaving us with the final, super precise answer of 23. Literally no decimal points allowed, all because our least precise original number, 13, didn't have any. Pretty neat trick, right? And that brings us to the end of our rulebook. Whether you're counting trailing zeros with a decimal point, finding the least total sig figs for multiplication, or drawing that hard vertical line for addition, what we are really doing is managing the messiness of real-world data. Numbers in science aren't just abstract ideas, you know. They represent actual physical measurements, and no tool is infinitely perfect, which leaves us with this final provocative question to think about. Does the illusion of perfect precision actually exist in the physical world, or are we always, in some small way, bound by the limits of our tools and the rounding of our significant figures? Thanks for joining this explainer, and keep questioning the numbers around you.